So day 2, it's Soil Life Summit, guys. Woohoo! I really think today is going to have some of the most impactful information. This is going to be a day that you go back and study when you go and you get the recording afterwards. I think there's going to be the most impactful stuff said here out of anything at all. But going back to David, whenever I go hang out with David to go pick up some of his products, we found David because we had seen Elaine Ingham conference one time, and she had a pre-brewed compost tea, a 1-gallon pre-brewed compost tea in a box, and she was selling it for like $150. So we saw Elaine Ingham was doing these pre-brewed compost teas, and we're like, well, there's technology out there, there's knowledge out there, and there's got to be other people doing this. So Rich, our fearless leader, obviously is amazing at researching stuff, and found David Olsen right in our backyard, who's been doing pre-brewed compost teas and microbes for a really long time. So that's how we got to know David, and his father, Gus Olsen, produced the first microbial inoculant on the market. I'm going to mess up how I say this, but what did you guys do on the market?
Yeah, we used probably the first commercial biological inoculant was about 35 years ago. My dad developed his first product about 25 years ago.
Wow. So that was what really got us involved with them, because they've been doing this for a really long time, and somebody who's been doing it for a really long time has got a dramatic amount of knowledge and experience. So whenever I go hang out with David, I've nicknamed him the Microbe Man, because I feel like he understands how he can talk to me about microbes, and I really get it. There's a lot of points of confusion and clarity. You know, you have a question, you get an answer, and there's just confusion. And then you get through it, and you apply it, and afterwards you get to a moment of clarity. And I think that's truly the point where we need to be to learn, is get through that confusion and get to that clarity, and really helps us get to the place that we need to be. I want to tell you guys, if you can, please come closer to us if you want to. That would be great. I know you guys are back there ready to take your notes, and that's perfect. So if you're comfortable where you're at, thank you. Couple other little quick things. We have a couple of lost items in the front. If you guys find anything, please bring it to the registration table. And if we didn't get your email, if you bought a ticket last second, please go to the registration table, because they're trying to get everybody's emails, because we really want to make sure you guys get the recordings of this afterwards as soon as possible to be able to apply that and get to those confusion, clarity moments. So yeah, I'm going to get the heck out of the way and let David do his presentation, which is going to help us start out on building soil and going forward. So I'm going to shut up here. Have fun, David.
All right, thanks. Well, good morning, everybody. Welcome to day 2 of the conference. And as Tyler said, I'm David Olsen, Sustainable Growing Solutions. We make microbe inoculants and commercial fertilizers, mostly oriented towards microbe food. So we produce all of the biological and fertilizer products that Grassroots carries. So in the breaks, I'll be over there. So love to talk about microbes. That's my shirt today. Ask me about my microbes. And that's what I like about the group that we've had here today. Everybody's been extremely intellectually curious, attentive, and very open about sharing their own experiences, because nobody knows everything. Keisha made a really good point about that yesterday. So we're all just kind of putting together pieces of a puzzle. So what I'd like to do is share some of those pieces, or the things that I think I know right now, I want to share with you. Some of my opinions may change over time as we learn more, and the rate that we're learning is astounding. Not just us, but I mean just as a community and understanding the relationship of microbes and plants. So a little background probably is helpful as context for the journey of the perspective and the approach that we use. So I'm a 6th-generation farmer. My family farm is 173 years old now. So it teaches a very, very strong sense of stewardship from birth. And it's pears and apples and kiwis and open grounds, so we have a bunch of different vegetable and row crops that we've grown over the years. So hands-on experience with a lot of different crops. So we started working with our first organic inputs about 45 years ago. I was at an age where I did a lot of the trial work, so a lot of hands-on experience with that. What it taught that that stage kind of taught us a lot about the fact that a lot of these inputs work better together. If you use them, in isolation or one thing at a time, you may see a benefit, you may not see a benefit. It's really kind of inconsistent. But as you start putting these pieces together, it starts to work much, much more reliably. And it's not just a 1 + 1, it's a 1 + 1 = 4. So about 35 years ago, we used our first biological product. It was actually a spin-off from NASA. It was a complex of microbes they're using in their space toilets. My dad developed his first biological product about 25 years ago. It was about 12 different species. They were really intelligently selected. We learned a ton about microbiology and how things work in the soil from that, because sometimes that product would work just spectacularly, and literally on the other side of a fence line, nothing. Wouldn't see response at all. So what we started to learn was that the importance of how soils work is as a community, and that if you're supposed to have 1,000 or so species of microbes in a gram of soil and a billion population, and if you're working with a production soil that is, say, just a small fraction of that population, both diversity and population size, throwing a dozen species at it doesn't repair the function of the soil, or at least reliably or sustainably either. So that really drove us to thinking about restoring the entire biology in the soil, not just a few selected species. As part of my early career, I had an airborne multispectral remote sensing company. We used it for crop diagnostics. So I've done, on-the-ground diagnostics of crop production. Remote sensing is really good at finding problems, but not really very good about telling you exactly what the problem is. I did probably over 500,000 acres of on-the-ground crop diagnostics, using that as a tool on probably 50 different crops. And so one thing that I learned through that process was we weren't taking care of our soils. At the time, I didn't even know what that meant, but for the most part, we treated soil like something that its only job was to keep the plant from falling over. And the chemistry of the soils was all screwed up. And as we started to understand what the production problems were, it turns out most of it was self-inflicted, either through over-fertilization or chemical imbalances that were just not being addressed in the soil. So that kind of gives you the background as to how I got to where we are, and what our overarching philosophy is, which we've kind of landed on is like, if you build the biology in the soil and you get that soil functioning correctly, the microbes and the plants evolve together. What they do together is extremely intricate. The number of interactions and the amount of value that the microbes create for the plants is substantial. So if you start restoring that population and you make sure that the microbes have the building blocks to deliver the nutrition to the plant, then things start to kind of take care of themselves. So it's just this kind of positive reinforcing loop of making the plant healthier. The plant has more excess photosynthates to exude out through the roots as sugars, but also with signalers embedded in it that direct the biology to deliver to the plant what it needs at that time. So of course, the nutrients that are needed at different growth stages change. There's high peak demands that happen at certain growth stages that the plant is really compromised if it doesn't get. So if you've got the biology and the plant working together, and there's the resource materials in the soil for them to work with, those get delivered. And it can really overcome quite a bit of imbalance in a soil. So say you have a base saturation of some cation that is really causing you deficiency in some other competing cations. The biology, if you give it a chance, can make up for a lot of that. So I guess I should probably start the presentation because there's at least some people here now.
I also have a jar of some Donnyburger that I'm going to start passing around because it's the best weed I've ever grown in my life, and it's all with David's products.
Cool. Okay. Okay, so here's a quick overview. So I want to talk a little bit about what the functions of the living soil are. Casey and Keisha did a great job of bouncing off of that. We're going to have, over these 2 days, at least 3 hours of talk about microbes, and you'll be surprised how little overlap there's going to be. Not because we disagree, but because it's just a big topic. So what are the functions of the living soil? What's the problem? What do we have to talk about? And then a little bit about how to build living soils. I'm probably not going to spend a lot of time on that because there's so many people already doing that here, and I think that the audience that I was wanting to talk to on that topic are the type of people that are not here. So maybe we don't need to spend a lot of time on that. And then probably just talk a little bit about some of the applications, the opportunities, the products. I'm not going to make this a commercial, but I am going to talk about the products in context of how and when we use them. Don't care if it's our products or other products, just want to show you how easy this is. It doesn't have to be hard. And once things start to work together, like what Scott was saying, when that plant hits the next level, a lot of things come together, and growing gets fun and really, really rewarding. So what are the functions of a living soil? How about I go the right way?
Do you have the blue?
It's harder than they say it is.
Oh.
And you could have it upside down. That's why we got the blue piece of tape on there.
Okay, so as I said, microbes and plants evolved together, so their relationships are incredibly intricate and profound. So there's nitrogen fixing and nitrogen cycling. One of the more important things that I think that the microbes are doing is delivering nitrogen to the plant in amino acid form. And that has a number of benefits we'll talk about later. Phosphorus and potassium solubilizing. Probably one of the most common complaints that I get from our growers, or things that actually bring growers to us, is they are just sick of having soil tests come back that say they're just way high in their phosphorus, and plant tissue samples that come back, or sap analysis that come back and say they're deficient in phosphorus. And every year their PCA says, well, we should put on more phosphorus. And the grower's like, we do this every year, and we have the same outcome. This is crazy. So what's missing when you have an adequacy of something in the soil and it's not getting into the plant, that's the definition of a biological problem, because the biology is not there, it's not mineralizing that material and not delivering it to the plant. So by restoring the functions of a living soil, we start to cure those deficiencies and those ridiculous expenditures on fertilizers that we're just not getting return on. Of course, microbes also do a cytophore function. Cytophores just means iron carrier, but it does cover all the cations, so it chelates all the cations, so potassium, calcium, manganese, magnesium, copper, iron, zinc. It has a chelating structure on the body of it, and actually that structure is the most powerful chelating force that has been documented up to this point, so it's extremely powerful. And then in addition to that, the biology in the soil is part of the immune system of the plant, so it protects from plant pathogens. So Keisha, I think, pointed out that you don't have to get rid of all the pathogens in the soil, you just have to have them balanced with everything else. So I don't know, maybe we'll talk about quorum sensing later. It's kind of a big topic. I could spend an hour just on that. But if you have enough of a balance of the rest of the biology in the soil, you will have no problem with those kinds of pathogens. And there's all sorts of different methods or modes of action in which that occurs. And of course, microbes also produce plant growth regulators. So all the physiological processes in the plant that come at different plant growth stages require plant growth regulators. The plant produces some of those itself, but a large part of those actually come from the microbes. And naturally produced plant plant growth regulators are much more important to the function of the plant than, say, adding artificial ones. And I think I'll give you a caution maybe on that shortly. Okay. I had a really cool video that's been done of some great research that shows how microbes actually feed a plant. This is not it because PowerPoint would not take that video. But I do encourage you to look it up on the web. It's fascinating. So, we've known, science, this is kind of how science works, where you see something and you suspect that there's something there, and then experimentally you might even be able to replicate it and prove that there's a relationship. It's like, hey, if we do this, we can have a predictable and repeatable outcome. But sometimes the knowledge of how things happen lags quite a bit from there, maybe even decades. So this is an example of that, where we knew that microbes fed the plant, but we didn't know how. Well, it turns out that, so this is a root hair, and the green are all microbes. And there's an opening here at the end of the root hair, and the microbes actually get sucked into there. In this layer right here, there's a superoxidase compound. And the superoxidase actually literally melts the shell off of the microbe. So now it's reduced, and then it'll go into some of these guard cells along the side of the root hair. So they are without a shell in the cytoplasm of the plant cell. So they're delivering their nutrients directly into the cell that way. So phosphorus to the mitochondria and all the other nutrients and functions, including the plant growth regulators. So that's how it gets delivered. The plant then ejects the microbes out, and they reform their shells, and they take the rat again. But at the time that they're actually inside that cell, remember that the plant puts out exudates that are sugars that feed the microbes. Well, there's also signalers that are in those sugars. About 2,000 chemical compounds have been identified up to this point. Only a couple of them have we, and when I say we, I'm talking collective science, not my company specifically. I don't do a lot of that original research. But there have been a couple of compounds that have been isolated, so it was like, oh, we know what the command is for nitrogen fixing. So we know what that chemical compound is. So if you appreciate the fact that there's 2,000 chemical compounds already identified, that's not just a signal, that's a language. And so that's why the microbes actually can respond to the needs of the plant and deliver to the plant what it needs when it needs it and in the right ratios. Okay, so what the heck is the problem? Well, as I said, a healthy soil should have about 1 billion microbes per gram. And unfortunately, most production soils that we see in commercial agriculture, and I'd have to say unfortunately in a lot of other cultures that we see, you have 1/10 to even 1/1,000,000 of proper population size. And so what it's doing is leaving all these vacancies where bad things can happen. Nature doesn't tolerate a vacuum. And healthy soils should have anywhere from 600 to 800 species. That's kind of what's popularly in the literature. I'd say we're shooting too low with that. I think it should be a couple times higher than that, ideally. And when we look, again, we use metagenomics where we can identify the genus and species of what's in the soil. We'll find only a couple dozen species. And so these are broken, unfunctioning soils. And so all those benefits of what the microbe functions are that I just listed, the plants are missing out on that. And I guess I'll take a sidebar here on this topic of a plant has a certain amount of genetic potential. You can't make it do more than what it possibly could. So it changes our mindset to say, oh, what our job is to make sure the plant has got what it needs at every moment. Because anytime it doesn't, what we're doing is we're eroding that potential. So when I hear somebody talk about making yield, it almost makes me laugh because that's not how it works at all. You make yield by not screwing up the yield. So our job as farmers is to screw up the genetic potential of the plant as little as possible. Well, I'll probably will get that into that in a second. Oh, okay. Yeah. So poor soils are the most common mistake that we see. There's so many other people talking about this. I'm probably just going to gloss over it because I'm spending too much time. But stuff you get out of a bag from your big box store, most of those soils are just terrible. I think, again, I'm talking to the wrong crowd for this because I think you're all way past that. And I see what people have to offer here in the other room. This is what we're looking for, and that's not the source of the problem. So, with microbes, time is your friend. It's important to give them time to be able to do their job. Don't expect things to be instantaneous. Instantaneous things are when you are putting on, say, ionic forms of fertilizer that are already bioavailable to the plant. I believe, and I don't have anything to back this up other than observations in my gut, that synthetic fertilizers break the relationship between the plant and the biology. Nothing in nature works without some level of reward and motivation. And so, if the plant's being treated like a sponge and everything's just kind of ionically there in the form that it needs, is like, why would I feed the microbes? Why would I have a relationship there? That's an investment in energy. And so as soon as you start using those synthetic fertilizers, you start to lose that functional relationship with the microbes, and you start to lose population size, you lose diversity, and I think I'm going to skip the rest of these. Maybe I'll just bounce off them real quick. Building a great soil is the first foundation step because you want to have the biology have the building blocks it needs to be able to deliver to the plant. So, we want enough water holding capacity. We want enough diversity in the texture of the soil. We don't want to have, a skewed pH, or we don't want to have base saturations or the absence of something, entirely. It's like the microbes can't deliver something that's just not there. So pay some attention to that. We've got some tools for that. Other people have tools for that. But the idea is to kind of preload the soil as you're building that biology way before you plant. Get your cover crops going and give the microbes time to do their job. By the time you put that plant in the soil or that seed in the ground, you'll have the biology there to support a successful plant. Yeah, cover crops are important. There's some fun things you can do, and actually this is a good group to talk about that with. So of course, you can play around with doing different pH zones in your soil. You can put a pH zone in an area where the plant won't grow into until later on in its growth cycle, and you can kind of load that with some of the nutrients it's going to run into, and you can bias that towards making those nutrients more available, so that's kind of fun. I also really like layering in usually dry plant materials and things as a layer in the soil, so what it's promoting is this kind of mycelial mat, and it acts like a big sponge. And so it gives you more water resiliency. It gives the microbes a great way to be able to move around. The fungal component is the hardest part of the soil to really get up and functioning. This gives it a really good platform. It also helps water lateralize. Don't get carried away because you don't want to have stuff breaking down and off-gassing like methanes and things like that. So don't use green materials, things like that. But if you build a good soil to start with and you stock it with biology, good things are going to happen. So there are lots of opportunities to put microbes into your program. So as I said, we inoculate the seed or inoculate the soil at bed prep. We inoculate seeds. I'll talk about more of that in a minute, so I won't spend time here. We do soil drenches, so if you've got a transplant or something like that, we've got inoculants for that process. We top dress various things throughout the growing season. We put a lot of materials, biology and microbe food into the irrigations. We do a number of different foliar sprays. I like to inoculate the cover crop and also the crop residue from the crop for decomposition. And I like leaving the roots actually in the soil because as those are broken down, those become the highways for air exchange in your soil, water movement in your soil, and even a free path for the roots of the next crop. So lots of opportunities to integrate biology into your growing program. So it starts at germination. Interestingly, and this is fairly recent scientific literature, it's been documented there are up to a couple thousand different species of microbes that actually are inside seeds. They aren't always there. They're there when that seed is pollinated and when the seed is formed, it has to be in the canopy there. So it's important to have a healthy biology in the canopy of the crop in order to have a seed that has biology in it that's going to assist in the germination and stand establishment. And it becomes a key part of, obviously, what would become part of your rhizosphere. So I see a lot of mistakes, so sterilized canopies, so we don't get that internal biology. Seeds germinated and either sterilized beforehand because they're worried about viruses or something like that, or germinated with sterile liquids. And that's just missing a tremendous opportunity because the microbes do a ton of stuff for germination. And here's an idea as to how you might, I think Tyler has talked a little bit about how he's cracked some seeds using some of our biology, so ask him. So when a seed starts to germinate, it actually exudates through the shell, and basically an invitation for the resident microbes to come colonize it. That's an important relationship, is that that biology goes with the plant as it grows, brings its community with it. The microbes and the metabolites that are there actually put out enzymes that soften the seed coat, and so that allows more moisture to get into the seed. They also produce some enzymes like amylase, which convert the starch in the endosperm into sugars, which is the energy source for the seed. I don't think I'm going to dwell on this too much because this could be a very long topic, but there's lots of different plant growth regulators that the microbes are bringing to the party, and they do essential things in the germination process of the seed. So everything from activating the seed to germinate, or stimulating it to germinate, to cell division, cell elongation, nutrition, and then some of the other plant growth regulator functions for developing the root system. So when we've got the microbes functioning, what are the benefits in seed germination, what are the benefits that we see? Well, we see things like increased seed germination. So if you're growing hemp, and you've got 1,000, I'm not sure how many seeds you have per acre, but I'm going to guess it's probably easily north of 1,000. If you can improve the seed germination rate by even a few percent, it's like, hey, they're not even out of the ground yet, and we've already made a several percent improvement in what the overall outcome is going to be. When we have the microbes contributing to the germination process, we see a much faster and much more uniform germination and emergence. So we've done some emergence studies with things like corn, and there's really fascinating work that's been done on that, where they will look at the first emergence of a corn seed, and they'll measure which ones emerge every 24 hours. So all the ones that germinate or break through the soil within the same first 24 hours, those are the ones that have the highest yield potential. If anything emerges more than 24 hours later than that first one, there's a 20% yield loss. And the next day, another 20% yield loss. So you could be, even by just being 48 hours late out of the ground, you've already lost 40% of your potential yield out of those seeds. So by having a faster, more uniform stand establishment, again, you've already made a lot of progress on not screwing up the genetic potential yield. And of course, because we have healthy biology, we have less seedling mortality, so things like damping off diseases, fusarium being a classic one. And of course, with the plant growth regulators, we're getting larger root systems. And the biology, of course, if you have endophytes that have colonized in the roots, then you are multiplying the surface area in which the roots can mine water and nutrients. So you can have as much as a 50% increase in the volume of the soil that you can effectively get water and nutrients out of just by having that fungal associated endophyte relationship. Okay, so the second most common problem that we see, and this is commercial agriculture as well as cannabis, is over-fertilization. Man, do we shoot ourselves in the foot. What happens is you put on too much of one thing, it gets in the way of something else being able to be picked up. And the plant will actually create tissues that are compromised in terms of their integrity and function because the plant substituted one nutrient for another just out of desperation because it can't get it. So when you get those weak structures, one, they're physiologically inefficient, and they're also vulnerable to pests and diseases. It's exactly that kind of imperfect structured material or plant that invites pests and diseases. So our philosophy, and I mentioned it earlier, is that we want the plant to dictate what it wants, when it wants it, and we want to have the microbes deliver that. So we call that microbially delivered plant nutrition and plant-directed health. So the microbes can make up for a lot of imbalances in the soil, but obviously the less they have to make up for, the better. And we can cut way back on our fertilizers. So this is not the opening pitch I make to growers typically because it scares the hell out of them to tell them that they can cut their fertilizer back by half. So we don't usually start out that way. Usually that's like a year or two conversation. But we use sap analysis to show how we're getting more nutrition into the plant with actually less fertilizer being delivered. Oh, okay, so this is a case study. So this is us using metagenomics. I'm just going to assume everybody know what that means. Not seeing any nodding. Okay, all right. Metagenomics. So it's where you take in this case, we're taking a soil sample, and you strip all the DNA out of all the life that's in the soil, all the microbiology, and you run it through a DNA sequencer. So you end up with this big database of all the DNA string. And then you compare that DNA string to a database where you do a pattern match, and you say, oh, well, this pattern matches this particular microbe. So what it allows us to do is come up with a list of the genus and species of the microbes that are in the soil. And then we can match that to what the function of that microbe is. So what we did was we took a soil and we did our regular program, just one application of a couple gallons of our microbes and some of the microbe food. And we looked at the function level of the soil and it's like, okay, well, how much are we moving the needle on this? How much are we really improving what the biology does? So we had a 190% increase in the number of nitrogen-fixing microbes, A 420% increase in phosphorus solubilizing ones. So again, plenty of phosphorus in the soil, wasn't getting into the plant, now it is. A 94% increase in species diversity, a 73% colonization success. So we look at the species of microbes that are in the product versus the species that have successfully colonized in the ground. In this case, we had 73%, which is a hugely high number because microbes colonize sequentially. There's ones that are good early colonizers, and there's ones that will not colonize until you get to a more full and balanced microbial community. So seeing 73% was, for just the first application, was very, very pleasing, very surprising. A 270% increase in cation chelation. So again, we're getting the nutrient potential from the soil successfully delivered into the plant. 500 times increase in plant immune response support functions from the microbes. So there's systemic acquired resistance and induced systemic resistance. Two different types of functions that microbes do in support of the plant immune system. It goes farther than that because they also produce some of the materials that the plant uses for its own defense. And that's particularly apropos within the cannabis world because the resin in the plant is part of its defense system. So as the biology is delivering building blocks for that, we're also building up the quality of your end product. 540 time increase in chemical residue degraders. So as we're cleaning up that soil of residue pesticides and herbicides, some things are very persistent in the soil. And the things that are the most persistent are obviously the hard ones to break down. So they'll have like a benzene ring or something as its core molecule. That's not a solo activity. That's not a molecule that can be broken down by a single microbe. That's a clade. That's a community of microbes doing a sequential job of breaking those compounds down. So that's the advantage of having this full biology restored. 140 time increase in organic matter decomposers. So that means that we're much more successful in breaking down that material, denying overwintering habitat for pests, mineralizing those nutrients and making them available for the next crop instead of having them compete for nutrients against the next crop. And of course, we're successfully sequestering that carbon into the soil and the biology rather than having it oxidize and volatilize as CO2. A 93% reduction in plant pathogens. In this case, 5% of the fungal community of the soil before treatment was Fusarium oxysporum, which is not a good guy, and especially it's not, well, it can be a benign microbe if it's in balance with everybody else. But if you have 5% of it, you've got trouble. And it went from 5% of the fungal population down to a non-detect. Now, we don't kid ourselves that we extirpated that species. We don't need to, because nature doesn't work that way anyway. But we got it down to the level where it is definitely not a problem. And a 99% reduction in anaerobic microbes. Several reasons for that. Some of our products have a metabolite in it that directs the biology towards an aerobic metabolism. And also, as the biology is doing its job, doing physical structuring of the soils and improving aggregation, of course, we have better air exchange. Better air exchange, we have reduction in the anaerobic molecule or microbe community. So here's the next important part. Sorry, this is sideways. This is why I like, well, one of the many reasons why I like the New Age Labs SAP analysis is, so I just talked about what we saw in the soil, right? So we improved the biology that's in the soil. But what really matters is how much did that biology improve the condition of the plant? Well, that's what this SAP analysis is telling us. So this is a comparison of two different sets of SAP samples. I'm only showing the treated one here. And any of the percentage changes I'm showing are in comparison to the baseline, to the grower standard program. In our program, we only had 50% as much nitrogen applied. The savings in the cost of the nitrogen was enough to pay for the whole biological program. So the question that the grower would have is like, boy, did I shoot myself in the foot? By only putting on half as much nitrogen, did we end up nitrogen deficient? And the SAP analysis allows us to be able to quantify that and definitively say, no. We actually had, with half as much nitrogen applied, we had a plant that had a 20% higher nitrogen status. So we got more nitrogen in the plant with only half as much applied. As important as the improvement in nitrogen status was the change in the form of the nitrogen within the plant. So it dramatically reduced almost eliminated the ammonium form of nitrogen in the plant. Ammonium, I think Jenny talked about this yesterday about how ammonium can translate from the soil into the plant. There's another situation where ammonium is formed in the plant, and that's under water stress conditions. So if you have a plant that continues to do photosynthesis during day wilt, so late in the afternoon the plant gets hot, it closes its stomata, you see the leaves get all droopy. It continues to do a little bit of photosynthesis. As it's doing that, it is generating ammonium that collects within that leaf tissue. Ammonium is very attractive to mites. And so if you've ever heard that mites are attracted to stress plants, this is why. So again, this is another example of something that we've known for a long time, but only just recently have been able to start to explain why. So reduction of the amount of ammonium, super, super helpful in making a plant that has less growing problems. If a grower doesn't have to get out there and spray for mites, he's just saved a whole bunch of money and made a healthier crop, because every time you do one of those pesticide or fungicide sprays, even the pesticide sprays that don't directly adversely affect the biological community, and there's not a lot of those, most of them do, it usually stuns the plant for several days. It's just sitting there doing nothing. Those are lost, photosynthetic hours, lost productivity. So when we talk about screwing up the plant as little as possible, yeah, the less of that we do, the better, because that's just lost time. Same thing with nitrate. We reduce the nitrates by nitrate form of nitrogen in the plant by 56%. So that makes the plant much less attractive to biting and sucking type insects. And over nitrate conditioned plants are the ones that invite mildew. So if you don't have a lot of nitrate in your plant and it's more ammonium form, amino acid form, inherently you will have less pressure from mildew. Doesn't mean you won't have it, but it certainly makes it less inviting. There are other nutrient, I don't have time to get it. There's other nutrient status things that we can talk about that also make a plant much, much less hospitable to having mildew problems.
15-minute warning there, David.
Okay, thanks. Okay, so a little bit about us. We approach it a little differently, so we don't do micro products that only have a few species. We're really all about reestablishing the entire community. So for every beneficial function, we don't want to just have one microbe that does it, but a dozen. And we want to have them in extremely high populations. And commercial agriculture is a game of logistics. And a fresh, active biological product, I got to tell you, is probably the best quality thing you could do. But in commercial agriculture, it's not practical. And so we put all of our microbes into stasis, so that means they're no longer respiring. They put themselves in a protective coat. It actually makes them so durable, not only do they have a long shelf life, but they can be mixed with synthetic fertilizers and for the most part not have any damage at all. And so that makes it something that's extremely practical for the commercial grower to work with. Is like, hey, I had planned on having this application Wednesday, but you know what, it's not going to happen until next week. For our product, that's not a problem. For an active microbe product or active population, that would be a real problem. And then the other attitude, and you probably have caught this already, so we pay a lot of attention to what nutrients are required by the plant at each growth stage. And so there's some really high peak demands of certain nutrients that happen at different growth stages, and that same nutrient might be almost inconsequential most of the rest of the growing period. So we spend a lot of time thinking about that and timing the application of those materials in combination with the biology, so we make sure that the biology is delivering that to the plant at the right time. And again, screwing up the plant as little as possible. I won't spend much time on this other than we do irrigate apply. We also foliar apply. We have different sets of objectives. I think it's important to think of this as this is a process. This is not just a one-shot deal, one and done. That's not how biology works at all. With the foliar, one of the advantages of our products are when we're growing this really large population, I don't think I mentioned the population, so usually we have as many as 100 billion microbes, so that's 1 times 10 to the 11th. We have had batches where we've been over 1 trillion, which is kind of cool. But you want to, as you grow a population that's that large, you build up a huge amount of metabolites that are actually already in the product, and that's something that you only get a little bit of from fresh active culture. So that's something, when you apply it foliarly, you get a big pop out of that plant. So, I mean, the day after you do a foliar, you will definitely see it. If we are on a reduced fertilizer program in association with the biology, we like to do sap analysis with that. So it's like walking a tightrope, but with a net, because we can see what's happening and pay attention to the trend lines, so that we can get out in front of the nutrition. So it's like, hey, we're not getting towards the goals that we have for this next growth stage. So we're going to intervene, either do another soil application with something to address that, or a foliar. We change the fertilizer that we use and the food that we give to the microbes for between the vegetative growth stage and a different population, and food that we use for reproductive growth phases. The nutrient ratios are different. The tissues that we're trying to build are different. The plant growth regulators are different. So we are definitely playing into that and trying to integrate that into our program. So once you harvested, it's important, now you've invested in building this tremendous soil and all this biology and all this life. You don't want to throw that soil out. You're going to keep making this soil better and better. And all we have to do is just take care of it. So if you can, don't pull roots, either on your crop or your cover crop. I don't know how you feel about that, but if they can decompose in situ, they're leaving all this great stuff behind, all these pathways and highways. Don't leave bare soil. It just gets solarized. You lose all the biology in the top of it. Things oxidize, and just all sorts of terrible things. If you can, keep an active growing cover crop on things. If you can't, just put some mulch on top at the very least. And then don't forget to continue to feed your biology, because next time you come in and plant into it, you want to have this active, functioning biology that you're planting into. So don't forget to feed it at least a little bit. I recommend, at least an annual soil sample, where you're taking a nutrition profile of the soil, so that we can amend the soil. And we spend a lot of time thinking about, okay, what are the nutrients that we've removed with the crop? So at the very minimum, we want to restore what we pulled out of the soil. But there's also, continuous improvement. So, there are all these micronutrients and balances and things, so that this is the time that we want to work on it, is in the off season. You don't want to throw a sledgehammer in the middle of your production season, because it's just going to knock everything off kilter. So, if you're like, hey, I don't have any cobalt, I want to put some cobalt in there. It's like, don't throw it in the middle of your growing season. You might add a little bit at the end, because actually cobalt can break up some of the plant growth regulators that cause premature senescence. So anyway, there's exceptions to every rule. So yeah, keep your soil, keeps getting better and better. And if you do all these things, you really should have a fun and trouble-free grow. And that's one thing that's really rewarding for me that I've heard several times is the spouse of one of my customers tells me, thanks me for making being a farmer fun again. So, open it up to questions. How are we doing on time?
I think we got about 10 minutes.
Okay.
I was wondering if you could touch on quorum sensing.
Oh, quorum sensing, sure. Yeah, cool topic. So quorum sensing, some of the microbes put out volatile organic compounds. And if you put your shovel into the soil and you smell that rich, earthy smell, that's volatile organic compounds. And they use, so this is basically a gas that they'll put off. They use it for a whole bunch of different things. So quorum sensing, when people usually talk about it, has to do with a population of a species of microbes sensing what their population size is, and they can change their behavior when they get to a certain concentration. Well, that behavior change it's not a volitional thing. These volatile organic compounds actually turn on and off gene sequences in the microbe. And so they can both use it as a way to sense their population density, which they can change their reproductive behavior, or they can change what their food source is. So we talked about fusarium a couple times. So fusarium will say, hey, there's enough of us. Screw it. Let's just turn around and eat the plant. So that's most of the time when people are talking about quorum sensing. I should mention the turning on and off of the gene sequences is a methylation process that the volatile organic compounds directly turn on and off. So it's also used as a weapon. So one species can use a volatile organic compound to deny the ability of another species to reproduce, or deny their ability to produce a particular enzyme, which means that they can't compete for a particular food with them. So it's a weapon as well. And one of the strengths I think that we have with our approach of wanting to restore all of the biology is that a population never gets to that position where it's like, hey, we have a monopoly here. We can do whatever we want. So it's not necessarily about suppressing a population, but it's about suppressing the quorum. And so when we talk about the different modes of action of our product in suppressing pathogens, I think maybe our most important function is quorum suppression, instead of necessarily reducing the population of a pathogenic bacteria or fungi. Did that answer your question? Okay.
I had a question about the corn seeds.
Oh, yeah.
Would you cull all the plants that germinated after 24 hours so that you knew that you had a higher producing plant?
In a commercial context, no, but your home garden,
in a small
you might.
context.
Yeah, in your home garden you might.
Definitely,
Yeah.
for sure. If anything's popping up out of 24 hours, if I can negate it out, and since all the, yeah. So.
Oh.
Kind of had a two-part question
Okay,
about
sure.
seeds. Three-part maybe. If you had a fusarium contaminated seed, would you consider sterilizing it with hypochlorous and then inoculating it, or would you start over completely, like you're saying, and do a compost tea on your mother plant so that it was inoculated from the beginning?
I'd say that's any one of those options that you identified, I think, are viable. You could sterilize it and then come back and then repopulate it with beneficial biology. We do that all the time because there's commercial fumigants that get used in agriculture. So their intent is to sterilize the soil. Well, it's kind of a last resort. It's expensive. Obviously, you're taking the entire biology backwards, but we can, after a few weeks of that fumigation, bring in beneficial biology and reestablish that. So it's kind of analogous to your question. Oh, you know what? I wanted to say something about epigenetics. because it's important to our biology, but it's also important to what you'll see in the plants. So when Scott talked about that plant getting to that next level, some fun stuff starts to happen. So gene sequences in that plant will get activated that aren't ordinarily active. So you can have even a room full of clones. And I think, Tyler, you told me this story about, or maybe it was one of my other guys, where it was a strain and the person that propagated all those, so it's his strain that he's sold. And so he goes into the greenhouse, he's like, this is mine? I've never seen mine look like this before. It was a fantastic grow, but it was expressing pigments and growing behavior that typically weren't expressed by that variety. And it's because the plant was just super happy. A really easy example at my plant is there's a place where we clean out our tanks and a lot gets spilled out on the ground. There's a lot of clover there. You can find at least one 4-leaf clover per square foot there. And it's because that plant is so happy, it's like, I'm just going to put another leaf on. So that's epigenetics. That's when you know that you are getting to that next level and you're unleashing some of the you just never before seen genetic potential of that plant. We also use epigenetics in the manipulation of our microbe population. So this is another important difference between kind of a community-grown inoculant or culture compared to, say, a microbe inoculant that's lab-grown in a petri dish. What we do is when we're growing our populations, we challenge that population. We force them to do some of the beneficial functions that we want. I force them to fix nitrogen because they need it. I force them to solubilize phosphorus. I force them to do those cation chelation functions. So when you read about a microbe and it says, it can do all these things, and that's true, it can, but it doesn't mean it is. And so if you have a lab-grown microbe, it's never had any of those challenges. It's grown in an auger where their intent is to grow the largest population they can as fast as they can. It is not doing any of those beneficial functions when you get it. Now, when it gets into the soil, it may find conditions that says, hey, yes, I can do this, and that's beneficial to me, so I will start doing that. My population will land on the ground already doing that. So that's a huge difference in fitness in terms of getting the benefit out of the biology. So I just wanted
Scott has one last question here,
Scott.
and we're out of time.
Yep.
So David, we were talking about amino acids, getting the microbes to supply nitrogen to the plants as amino acids rather than nitrate and ammonia. If I want to take SAP analysis to another level, add another parameter that we monitor and break out this nitrogen breakdown, give me a parameter that I can look for in SAP that will tell the grower what they're getting in uptake from amino acids from microbes. Do you have a parameter I can look at versus just?
So I'm a little nervous that the SAP analysis expert is asking me for my opinion on
It's always a collaboration. You give me an aha moment and I'll make everybody else happier.
Okay, well, are you asking me about which amino acids or?
Well,
because that is important, which amino acids.
I think we could do an amino acid panel.
Yeah.
Certainly. But now you've got amino acids that are being produced by the plant and may not be distinct from the amino acids that are being provided by the microbes in the sap. So is there a particular parameter that might be unique to amino acids that are provided by microbes that would be separate from amino acids produced by the plants that we could focus in on, and look at that as a overarching indicator of microbial contribution to amino acids?
I'm going to say unless you had some sort of tracer that you put on to the amino acids that are being produced, radiological tracer or something like that, I don't think you would be able to sort that out because they're making the same amino acid.
Okay.
What I would be interested in exploring is, remember I was talking about the 2,000 different compounds that are being put out by the plant roots as exudates?
Yeah.
I would be very interested in getting a profile of what that is, because if we can start untangling what that is, that tells us what the plant's asking for. And so that gives us a much better job, or much better opportunity for us to, step in and make sure that that's being provided to the plant. So I think that might be so sap analysis of the roots, but specifically with the objective of looking for those particular compounds.
Well, I think that's the interesting thing. Now, this past year, we started doing sapping on actual root systems,
Yep.
particularly mostly in winter wheat and stuff. But if we sap the root and then we take that sap, not only doing the nutritional panel, but start putting that on a mass spectrometer and start breaking out the actual organic molecules.
There you go. Yep, so now it's just starting to build a database and starting to be able to match what the signal is to some later identified deficiency.
There you go.
Yeah. So
All right, guys. We're going to have to wind it up there. We pushed over by a couple minutes.